Alright, hopefully this works. Let's see. Are we online? All I see is a loading bar. Not sure if any of this works. Sound check, 1, 2, 3. Is this working? All right. Is the sound okay? I just lost the power just before starting. All right. So hopefully everything is sorted out now, and I hope the audio is okay. So today I'll be checking some of the boards for Hulk-3 codename Calibrator, which is essentially 5700A Fluke multifunction calibrator. And we will look if we can fix some boards, do some tests, and get some progress. At least this is the plan. And I have a few boards to test today, mostly resistance boards. That's where the focus will be. And then we can look at the REFDAC and see if we can get any improvement or operation in there. All right. And I'm not sure like what if the camera is switching is working properly or not. Okay, so that is working. So these are the bad boards that I would like to test and repair. So if you have some missing components, and the board on the right, this guy, is quite broken. It gives a bunch of errors. Essentially every range fails. So the board next to it is the same board, same A11 REFDAC board. So that have a couple of the mechanical damages. And then we have two resistance boards, A9 and A10 boards. So these are remains of my previous calibrator projects. And essentially the different donor boards that I used to test parts, remove some components for use on working calibrators. And now that I have many of the other boards, I decided to make a complete calibrator out of all this. So I can show calibrator itself. This is the unit, 5700 or 5720, it's the same chassis. So it's actually powered on right now. So you have the front panel and working. So we have front panel, the power supply is working, but other than that, this unit have just 3 boards, and it still have a lot of self-test fails. So we can run diagnostics and I can show you. So it obviously complains a lot, and I hope the video is actually updating. Yeah, now it is. Let me figure out what's up with all this. I used different computer for the stream setup initially, but it will take forever to set that one up. Let's see. Yeah, so it have a bunch of errors because some of the boards missing, and yeah. So let's get back to the boards. I can probably show a close-up on one of them. The connector on the wideband hole is a triaxial connector. So I had a couple of the ideas to try on this calibrator, and essentially to provide a guarded current output with some of the ideas to improve the lower ranges, because originally the range on this calibrator is not that low noise or particularly accurate. So what we can take a look is this resistance board. So I have a few of them. So on this one, as you can see, there is a missing network. So right in here, Z1. I bought this board originally to replace or repair my other board, which had this network cracked. So this board have some missing components, like relays are not present. So I took this Z network, Z1 network, nichrome alloy resistance network that used for some of the resistance output from the calibrator, moved to the other board, and this board was just sitting and collecting dust, waiting for a good moment to use it. So what I can do is to repopulate some of the resistors to mimic the original network values in this position. And obviously we can put back relays and plug this board in and see if it actually working or not. So everything else looking okay. I replaced this driver chip before and put the capacitor back in. So nothing other. All these relays are obsolete, so it's kind of hard to get them as a replacement. And the calibrator is filled with these relays. And we can see other network resistor, which is a CADOC. That guy on the between the red relay and the yellow relay, that is high resistance 100 mega ohm standard. So this is about this one, and this is a ohms calibration board. So it have the floating supply, have some control chips right there, relay drivers, and we have number of relays again. And these are 4 ohm resistors that combine together network to make 1 ohm output, as well as 1.9 ohm output. And we can see like this network right in here, it's actually damaged. I'm not sure if it's easy to see or not, but the cover glass that actually seals this resistors network from external environment damage and humidity and stuff like that. There's actually only a little piece of it is right there, and everything else is missing. So Obviously this resistor is damaged, and this is a 10 kilo ohm to 90 kilo ohm network used as a calibration transfer standard. And there is another issue with this board, is hidden behind this metal cover. We can just remove it. So everything looks fine at the first glance, but we can see there is a Z1 network is also missing. So it looks like similar to this, but a little bit longer, with a bunch of resistance values for this resistance compensation circuitry. So this is a 2-wire compensation current circuitry. So we will have to put something back in to replicate the original resistance values that were in there. All right. So this is about the resistance boards I have. And we can take a look on the REFDAC board. So here is the REFDAC. It's one of my other old boards that I was testing some chips and assemblies. So I have, there is a heated ceramic network together with the resistant network connected in there, and it was mechanically damaged, so I desoldered the assembly. So you can see this substrate. This is aluminum substrate with the op-amp. It's a buffer op-amp used to drive output voltages from the REFDAC. Some of the thermistors, some passives, and on the back side of it we can find a resistor network, which is epoxied to this aluminum substrate, and on the other side of that substrate we have the heater carbon resistor. So it's usually around 40 ohms connected to the edge pins, but this network was physically damaged, so this corner was chipped. I tried to replace, like repair with the wires. I can probably try to zoom in. Yep. So it's a little bit of how you doing. So while I got the wires connecting those pins on the top surface, the problem was that the heater connection that you can see on the back, so there was another connection right here, and it's obviously broken, so I cannot connect because you cannot solder to the graphite. And this is the another end of this. So very pretty and very fragile network, and this is that resistor. All those pretty network form different values. So they use a clear glass or quartz window to allow laser trimming of these resistors after it's sealed up. And this is the front of it. And you can see like there are different height components under the blue protective layer. Those are actually embedded passive resistors as well. So that's what was damaged originally on this board. And this is the reference assembly in here. Then we have ADC in this box on the right. So there is ADC. This is a resistor for ADC, some circuitry around, and this is 5700A grade version. So I don't know what else is wrong with this assembly. So we can just use it for parts at this time. and as well as this assembly that is still sealed up. I plugged it into the calibrator and try to test it, and it's give pretty much every error there is, like DAC monitoring errors, different even like 13-volt reference fault and bunch of other faults. So either some power delivery circuitry on this board is bad, or I don't know, maybe some physical damage to some power parts. We'll see. So either way, we can either use parts from this board to fix that board, or the other way around, whatever will be easier. So, and like actually this hybrid is covered with this plastic cap. This is essentially how they seal microclimate inside to keep the oven stabilized temperatures for these different assemblies in Calibrator. So let's go back to it and see what we can fix quickly. And I think will be probably easiest to work on this board first. So because like we just need to fix that resistor network, and then we can try this board out if it's actually have any chance of working. Everything else looking fine, a little bit dirty, but that shouldn't be a problem. And then we can try to look at this other resistance board and again put the relays back in, put the resistor network, maybe replace some tantalums. So that's the idea for now. I hope the stream health is okay. I see it's a little bit sluggish, but I'm not sure if it's actually technical issues or not. And hot air station, well, I still have the Chinese quick station, so nothing fancy here. And before we go, I can actually show what the calibrator is doing. So let's see if I can get that up. Yep. Wish I could adjust the brightness a little bit on the camera so it doesn't. It's flickering because of the 60 Hertz of the refresh of the camera is interfering with the refresh of the VFD display, but obviously it does not flicker in the, to the human eye like that. So right now I have in the calibrator I have just few boards, so I can show you. So firmware in the main CPU board 1.4, it's 5720A firmware. In guard assembly have revision A, and then from the hardware configuration I just have switch matrix A7, current module that is also A7, switch matrix is actually A8, and DC volt module A11. Yeah, high res oscillation module, that's the part of the A7. And we have a rear panel, that's it. There is no any AC voltage assemblies, obviously no resistance assemblies, and this calibrator is pretty empty. And the good part, we still can actually calibrate it using just 10-volt reference without resistance. So I did that yesterday and it did run, but today when I try to do the zero, it actually fails. So I can probably demonstrate that on camera. I run it just before the stream start like 5 times, and it failed with 2.2 volt zero fail, whatever that means. So probably there are some more faults and issues hiding on the other assemblies in Calibrator as well, which is fine. It's more interesting challenge to repair and troubleshoot. All right. I really like how the firmware of these calibrators is done. It's essentially very flexible, and depends on what assemblies you are running. It would not cause major fails, but will let you actually bypass missing stuff to run. Obviously, you would need still have minimum viable setup, which would require A11, A7, A8 and power supply boards to be working somewhat functionally sound, so it could have a chance to run at least minimum set of tests. So this is the same error that it was giving back. Couldn't cal 2.20 2509. And after this point you can only reset the calibrator, and it's 2.2 volt is generated together from A11 and A8, so could be some issue with A8 board. I do have another A8 board also broken, so we'll see. If we have some more time left, then we can try to troubleshoot this. Or it could be A11 board, so either way. And I can show you insides of the calibrator, so to indicate how it looks like. So I have essentially these two boards. So this is A7, A8. This is the DAC board. It's also have some label. So it was 200 ppm off for some of the ranges. And then we have two power supply boards. So this is a guard crossing board together with the with some of the linear regulators on those big heatsinks, and then we have the main power supply board to provide all the voltages from transformer into the DC voltages. So that's that. And we have some of the relays on the main board. So I'm not even sure that this main board is 100% functional. So it's kind of take all the bad parts and put it together into one box kind of project. But if we can get it at least working for some stuff, it would be a handy addition. All right. So we can turn it off for now and focus on our repairs. So I actually already looked at some of the values of resistors I need for those network replication, and we can take a look on that briefly. So let me get to the schematics page. So what I really like about older instruments, that they usually come with a very nice repair and service manuals, including schematic diagrams and assembly drawings like this. So owners like me can actually look at the different assemblies and attempt some repairs. Obviously you still need to understand what you're doing, but this information makes even starting attempts to repair something complicated like this calibrator possible and viable. So unfortunately in these days modern equipment is deviating from this practice, and now they're just expecting you to call the service department, charge you 90% of the new instrument, and hope that you will just pay and get a new instrument instead of replacing or fixing some possibly cheap and simple component in equipment you already own. So it's not environmentally friendly, it's not financially friendly, and obviously if you have a business depending on the calibrator like this, then you would still pay up. But for less critical applications, sometimes it's very viable to repair calibrators and equipment and other electronic devices instead of just filling the landfill with the hazardous materials waste. So I really hope that we can get in future some more service informations included with every device sold, but we can wish and hope and fight for it. That's more like a complex problem to solve. Okay, so this is one of the resistance boards, and I can show you that Z5 network is damaged on the board I have here, and also we have missing Z1 board, Z1 network on this board. So this would be, let me scroll down. So this is the A9 board, and here we can see Z1 bunch of resistors around these op amps. So 1 kilo ohm, 1 kilo ohm, 75 kilo ohm. What else? And then this network box in here for this 2, 5, 10 volt source for resistance calibration. It also have 15 kilo ohm, 50 kilo ohm, 11, 535 kilo ohm, and 3846 kilo ohm. So obviously we will need to replicate these values and connections if we have hope to fix that. And I bought actually a bunch of resistors, so I can show you the resistors. Nothing super special, just fixed resistors from DigiKey. And for now, the idea would be, so like this PTF 56, 1 kilo ohm, 15 kilo ohm, 3.83. It's not exactly the same value, but close enough, I think, for some tests. 11.5 and a bunch of others. So the idea is to make a network, like a makeshift network, using these single resistors, and then we can put it in a place where it's supposed to go, and test if that makes the board functionally working. Obviously the performance wouldn't be the same as with the original network, but for now we only care if the functionality of the board would be restored. and if it's working as it's supposed to be, then could in theory order some custom value resistors or even custom network for more adequate higher performance repair. But obviously if we put the resistors in and it would still fail to operate properly, then wasting more money on fancy resistor network would be pretty much premature. So that's about that. So what I'll do is just figure out which pins represent what resistor. I did already some preliminary checks, and should be easy enough to botch some through-hole components to replicate the expected values. So I'm just trying to set up the bench, and actually I already scribbled the network, so I can show you in a sec. So that's how the connection looks like. So we have few of the common terminals. We have 1, 2, 3, 4, 5, 6, 7, 8 resistors to populate. So we have 1 kilo ohm, 75K, 1K, 75K. This is actually two of the same. Then 15 kilo ohm. This is a common terminal for all these 4 resistors. Then 50K, 11535, and 3846. And then on the actual board, it also looks like that. So there is plenty of space to work with. All the through-hole footprints should be easy. Okay. Is there any lag with video, or is it actually in sync? Because I see pretty bad lag on my end. Yeah, it's about maybe like 5 seconds or so. On the camera I don't see any lag, and on the OBS I think everything looks fine too. Yeah, on OBS it's pretty much instant. Oh boy. So let's see, we have 2 1 kilo ohms, so I can get that. I think this is actually 10 ppm per degree resistor, so it's pretty fancy. PTF 56 series. I like this series a lot. So this is the part number. So we need 2 of these. Then I need 75K. I actually bought some 75K for some of the old LTZ reference modules I built years back. So this is also PTF 56. So it's 0.02%. I don't remember what's the temperature coefficient on this one, but I'd expect something relatively decent. So we have 275K. Now we need 15 kilo ohm. I think I had some of that. Let's see, 15 kilo ohm. Yep, there is the 15. It's 0.1%. It's lesser grade than TTF 56, but I think it will do fine for this initial experimentation. And then we have 50K. So for the 50K, I actually don't have the resistor, but I do have 49.9, and then I can put 100 ohm in series together with this guy, and this way we can get 50 kilo ohm, at least closer to that. And this is RNC 55 resistors. I believe if the writing is correct, then 0.1%. Probably even 49.9 would work, given some tolerances and calibration, but I mean from what the calibrator might expect. But we can just mimic exactly 50 kilo ohm as schematic says. And this is a 100 ohm. It's a MELF resistors, 0204. So I'll keep this packed for now, because it will be quite tiny and easy to lose. Then we have 11.5, and I actually have 100 ohm CMF 50 as well. They're a little bit smaller than PTF 56. Anyway, let's keep those aside for now, and this is 383. So this we can put the last step. So time to get soldering iron hot, and then we can try to cook a resistor network in here. And we can actually remove the bottom plate. Yeah, I see. It's probably a USB issue with the capture card. The frame rate is kind of slow. There we go. Just a metal shield plate. So there are also some of the tantalum capacitors in here. So like in this, 4, 5, 6, 7, 8 of them, and 9, 10. 10 capacitors, but we can worry about them later. but when I do the full repairs, I always replace all those old capacitors, because a lot of the time this equipment is running unattended for days and weeks and months, and I don't want to have them catching fire while nobody's at home. So that's that. No problems on the back side that I could see. So let's get started. Yes, the cutters are indeed carbide edged. There are carbide inserts on the cutting edges. I love them very much, and I have a couple of them. So they are super sharp, give very nice cuts, but obviously you cannot cut anything hard because the carbide will shatter. Not really, but they are not that expensive on the secondary market, so I just have a spare just in case. So let me. I really want to have this. The camera that is slow is actually my DSLR, so I think it's the connection to the capture card, HDMI capture card, that is choppy. Yep. I don't think there are any settings here that would have anything to do with it. No, pretty much the same. And the tricky part is that if I disconnect and reconnect, then I'll lose the audio. I mean, we still can try that. Yeah, I guess we can try it. One, two, three. Okay. Audio is back. Okay, now it's better, I believe. Hopefully it stays that way. Is the sound okay? No problems with the sound, I hope. 1, 2, 3. See if other cams work. Yep. Someday I'll find a nicer eBay special camcorder, and all these issues would hopefully go away. But not today. Okay. So my strategy with the resistors would be essentially make them standing vertically, and then we can just make T-junctions with the solder and go from there. So let's try that. So obviously I'll need to make sure I have the right values. So this is 75K, it goes right there. Then we have 1K, goes here. And yeah. So something like that. The part number for the cutters is RM576TX. In case somebody was wondering about what we were talking about earlier. Yeah, something like that, I guess. Obviously, right now I'm just forming the resistors, so I would know where what goes. This is 1 kilo ohm. And then we have 75 kilo ohm. Okay, I guess we can solder them now. And let me check something real quick. Backup power. Well, there is no backup power other than the source and voltage references. So I would need at least 4000 watts of the backup power for the main lab, because I have calibrators, DMMs, all that running non-stop. And each of the calibrators is around 200 watts, so plenty of juice. Alright, let's get to the resistance board back. Fume extractor is on. And before we go, I would like to make sure that the pins are correct, so we don't solder wrong resistor wrong place. So pins 1 and 2, 1 kilo ohm. Yes. I'll just solder one pin, so I can actually push something under the board, so I have the room for pins to go down. I don't want to have a resistor body touching the PCB, but I want it to be close enough. So now we solder 75K. And these holes are not big enough for both pins of each resistors to go in. So I'll have to actually solder like a couple millimeters away from the joint. I'm pretty sure in the network they have 4-wire Kelvin connection to all these resistors to limit the impact of the thermal coefficient of the copper or whatever material they use, which is obviously different than the resistance material inside of the network. Now I just grab this center terminal. Yeah, it doesn't look too bad. Support the corner of the board, so like other resistors don't touch the table. I also see op-amp replaced. This op-amp was replaced at some point. Okay, so we have 1K and 75 kilo ohm done. First one. And let's do a second one. Alright, now 75K. Oops. Doesn't want to go in. Need to cut the other end a little bit. There we go. I think I need a little bit more in. Yeah, something like that. Okay, well, half of the job is here is complete. I think it looks pretty reasonable. Actually, the second one looks better than the first. I can probably show you the close-up. And then we need to worry about that second network right there. Clean the flux later and see how it goes. The focusing on this camera is kind of weird. Are the PCB special material? No, this is normal FR4. So now a little bit more challenging job for the remaining of the resistors. So we have 15 kilo ohm, so that is pretty much straightforward. Double check the value. It's 15,00445 ohms according to my go-to meter. So close enough. Let's solder this guy in. So this is between pin 9 and pin 10. Pin 9 and pin 10. And pin 10 is our common, where all the connections are relative from. I think it's a little bit too long. Now it's more like it. Now the next one is 50K, so I need to solder that 49.9. Actually, I can make this network a little bit longer, or should I say taller. So I can have the room for those shenanigans with 100 ohm resistor. So this is 49.9K. I'll just apply some solder. And I'll need to cut it pretty short. And now I need to put that 100 ohm, so I think I'll put the CMF 50. It's a little bit easier. CMF 50 is essentially similar looking style as PTF 56, but smaller, because they are rated only for the 0.25 watts of power instead of 0.1 watt, I believe. Or maybe the power is the same, maybe their voltage rating is different. Anyway, they are smaller. So I'll just wrap this pin around, and then, and what I do then, probably go down there. Yep, something like that. Yeah, I think that works. So I have the resistor going down and to the common pin. I grab the pin when I am cutting, so it would not shoot up into my eye. Okay, well, something like this. So we have 49.9 kilo ohms in series with 100 ohm, that little guy. And now we need just two of the resistors connect to that second pin, pin number 10. So that should be trivial. Hmm. Alright, let's get back to it. So now we need to find the next one is 11.53535. I don't know why Fluke specified this specific value. I guess I can just measure a bunch of these ones, which are 11.5, and then we can see which one is the closest, I guess. I'm sure Keithley 2002 in a 2-wire mode will tell me. Well, this is 0.1% resistor, so they are pretty accurate. So this one is 11.504, 11.503, 11.506, 11.504, 11.490, 11.499, 11.499, and yeah, the lead resistance is not that important here. 11.505 and 11.496. So I could do the same bodge with the extra, like I guess 30 ohm resistor, but I don't think it really matters. Those values sounds like they are ratio values, so I'll just pick the highest one out of these 10, and yeah, let's take this one and roll from there. Because this is, I expect this to be temporary test resistor network anyway, so as soon as it works, that's all I want to see. I think I need a bigger bend radius for this guy. Actually, something like that. There we go. Is just gently hit the pin up and then apply some solder, and off she goes. Now we need to have 3846 kilo ohm. I have 383, 0.1% as well. Let's measure 5 of these. Pick the closest one. 3826, 3826, 3827, 38279, 38269. Well, I guess they're all about the same. Last network, and then we can I guess, plug this board in, see what happens. There is actually also this pin is damaged, not the pin, the pad on the PCB. So I'll need to make sure the connectivity is okay according to the schematics. Because this is a 6-layer board, I believe. No, it's 4-layer board. So there is a connection to this resistor somewhere inside, on either second or the third layer. And need to make sure that that connection is still fine. Pad from the back side is fine, so hopefully it's okay. So this connection should be going to the drain of Q3. It's a little switch. Let's see the Q3, where is it? Okay, it's there. I don't know which pin is drain. There are no pin numbers on the PCB, but we can actually look at the... So the source is, there is a Q2 as well next to it, and they both have connected source to the pin 11, that 50 kilo ohm resistor. So we can see which pins have connection. Yeah, I can actually see on the PCB. So this is pin 9, 10, 11. So that is that, and I believe other end should be here. Yep, shows 0 ohms. Should be fine. Okay, I think we have our network. So, this is what we got. Doesn't look pretty, but to do the job. I'll just clean the flux on the back. And those transistors I was talking about is this Q2 and Q3. And then clearly this op-amp is much newer, from 2008. And there is actually some flux around the pins. And actually, since we are at it, I can show the damage on this network. The network itself looks fine, but a piece of glass that's supposed to cover the whole resistor. There is a little chip on the other side, but that shouldn't be too bad. So we can actually check this resistor. Should be 90 kilo ohm at that finer pitch 2 pins, and then 10 kilo ohm that bigger serpentine on the right. All right. And when I'm putting board down, it's actually not put down, but there is a piece holding of the cable, so I don't apply any stress on the resistors. So the 10 kilo ohm reads 9.99934. Probably even show it. So let's see. So I'm measuring the bottom resistor. Whoop. So this is pretty good 10K. And then the other end is 90 something. 90.9, well, bouncing around 90.01 and 90.009, I believe, because this is two-wire measurement. And I have the meter configured for a fast measurement. Alright, let's plug it in and see what happens. I think I can turn off the fume extractor. Availability of relays, well, second-hand only. They are obsoleted long time ago. And the question, those networks aren't filled with the atmosphere? I wouldn't see the easy way to fill them. So I don't actually know. So I can put the back shield in, just in case. Not that it really matters right now. So let's plug it in. So this board is plugged the opposite way, right behind the A8. So with this board I should be able to generate 1 ohm, 1.9 ohm, and that's about it. And it should actually detect normally, because it actually needs a second board, this one, to provide all the other resistance values. So at least we can run now, turn it on and see if we can get any reasonable values. All right. So instrument boots up. Try to mess with camera a little bit, or I can use not a webcam but DSLR, if that gives the better value. Let me see if I can get it to reposition. I have too much glare. Nah, we can focus about that. Actually, we might need both if I want to show the measurements by 2002. Yeah, maybe this is better. So let's see if the board is detected. Instrument config, show hardware. So we have ohms module. That's a good start. So the board is detected. We can try output 1 ohm. And we indeed have some of the output. And I guess I can move it to the other meter. So we can check the output. Oop, not so fast. So let me connect the output of the calibrator. To the DMM, and then we can see what's what. And obviously all that resistor network circuitry wouldn't be doing anything right now, and reason is because it's used only for calibration, I believe. So it wouldn't be changing anything even if it's not working right now. But at least we can have the relays checked. I'm pretty sure I will need both of the resistance boards for calibration check. And by calibration check I mean working of the transfers, not actually accuracy check. So let me turn output on, and I get nothing. Okay, hold on. I might have the wires. No, wires all connected. How about 0 ohms? Nothing. Okay. So it could be that it would go, the resistance might go through the other resistance boards too, even for these lower values. I guess we can just continue soldering and fixing the motherboard. Alright, that's that. You don't see any smoke. It's always a good start. You can run a self-test, see if there's anything changed. Let's see, list table values. Yeah, this is not useful. Self-test. Let's go. Wonder if I can. Yeah, it always complains that like, oh, A12 is not there. That's fine. It's fine. We don't have any AC voltage boards. A16, we don't have that board too. A14, don't have that. A12, 13 not responding, we don't have it. Dark digital. This doesn't work. There's quite some glare. Let's see. The readout on the left is actually dim glass, but actually I think this right screen dot matrix display is overdriven and the filament is a little bit too bright. So, and that might be, it's too bright to be normal. And I have a bunch of lights around for the live stream video. To be honest, I don't really care. As soon as I can see the reading, that's fine. So I guess we can put the resistors back. Not the resistors. Relays on this A10. And then go from there. Okay, A12 or A13 not responding, that's fine, fine. High-res oscillator. C5. Well, self-test didn't give any errors with the resistance. Actually, it didn't give any errors related to installed boards at all. So I guess that's fine. We can try calibration 0 just for fun. Probably will fail with the same point. And let me prepare relays. Yes, relays I got. And actually resistors for this A10 board are, I got them before. They are much fancier than PTF56 we saw earlier. So maybe this will be a little bit more exciting. And the resistors I need for the network replication are, let's see, Z1 network. So they are 19 ohm, 171 ohm, and 1710 ohm, so 1.71 kilo ohm, as well as 10 ohm, 90 ohm, and 900 ohm. So there are 6 resistors that I need, and I believe I have them all. So let's see. Did it pass that point that it was failing before? Maybe it's because it's cold? Not sure. Alright, meanwhile I'll try to fish out those resistors from my secret stash. this input path, DCI zeros, that's already beyond the DC voltage calibration points. Okay, it failed 22 milliamps, but maybe because it doesn't have the resistance board, second one. So let's go and turn this one off and find the suitable resistor. It's a lot of gold in the photo. A lot of it. So the values that I need, where is the schematics? So the values are these 990, 10 ohms, and then this 1710, it's 171 and 19 ohms. So this is actually the same network, Z1, and I'll need to replicate them. So let's see which one is this one. That's 1K. Here we are. I believe in this box. This is VHP 202ZT resistors. So this is 171. This is 1K71. So now we need, this is 90 ohm. This is also 171K. This is another 90 ohm. This is 19 ohm. This is 900. 90 we already have. Yeah, 90 we already have. 19 ohm. Okay, so we are missing. We have 900, we have 90, we have 1.71K, 171, we have 19. We don't have 10 ohms, so I need to find the 10 ohm. I think it might be in a different box. Resistor has 80 ohms, 1 kilo ohm, 100K, 1K, 100 ohms, 40 kilo ohms, and then 10 Ks. Okay, let's look elsewhere. So this is as fancy as they get. I have 10 ohm S102, so we can use it as a backup if we don't find the fancy one. I have actually a bunch of them. I think these are eBay specials. I have this huge, oops, VHP4, so I don't think I have enough room there for that guy. This is another 10. I have actually quite a few of them. Let's look on a few other locations. So I have 13 kilo ohms. It's not that. Wow. All right. What we can find in here? Kilo. Oh, there is 10 ohm. I think our mission is solved. Have another 19 ohm, and I have another 10 ohm. So we have actually two candidates. This trimmer, 5 kilo ohm trimmer. Okay, I think we have enough for this implementation. No, most of those resistors are not from eBay. Hello, DevPom. How are you doing? So, now the task is how we can put all these fancy resistors in this room. So there is actually plenty of room. Let's figure out which one goes how. So I need to find, where's the schematics? There it is. So I'll just do the illustration with all pins and do the like a kind of a map, so we can figure out how each of the resistors will connect. right. So how many pins we got on the board? So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 pins with one empty spot. So we can draw that same here. 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Then there is an empty spot, and then there is one more pin. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. Okay. So now we need to redraw the schematics representation. So this is a little bit interesting, because this is why they have 6 resistors but 14 pins. The reason is Kelvin connection to the resistive element right in the network. Obviously we cannot replicate that in here, so we'll have to be innovative a little bit. So here is the first one. This is 900 ohms. And it connects to pin 2 and pin 3. So it looks like that. And then this same point used to connect 900 ohms to pin 5 and 4. So this is essentially what they're trying to do. And then this same point goes to 10 ohm, which connects to pin 6 and pin 7. So they always, the reason for this is always have a 4-wire connection to each of these elements. So obviously with our 2-wire resistors it would be quite challenging, but it will be interesting to see if how much of the extra copper connection would ruin the temperature coefficient of this network if we are to build it from 2-wire resistors. Alright, let's continue. So this is done. This is 90 ohms and this is 10 ohms. Now we need to draw another one, which is completely separate. So it's 8. Probably easier to draw it like this. So this is, we have 19 ohms. And then connection between 10 and 11 goes here. And then we have 171 ohm. Connection goes there. And then we have finally pin 14, kind of separate, just single wire to 1.71K. Alright, this is what I need to replicate. So how we can do it? Now I could essentially, let's see, so I can put, where is our 900 ohms? There is 900. One pin connects just there, and one pin connects to this middle point. So either I can have the wire, extra wire connected right to the resistor body, which would may cause some issues with the resistor, because then I'll be overheating it. Or I can have just one wire connect to these two pads on the PCB side. So we have essentially 3, 900, then we have 19, and this is actually 10. So this is our 10, and then we have 19 ohms, 1K7 and 171. So they also, if we just line up all of them in one line, they occupy a lot of space, and I don't think we have enough space in here. Yeah, definitely. So I'll need to make a little optimization for room. Or we can just solder it and see what happens. So let me think about it for a second, and meanwhile we can just swap the relays. Not swap, but install. So I need to clean a few holes up, and then we can get on with installing a resistor network. First need to add some flux, some solder and flux, so I can have a good thermal connection. Now I can just poke through the hole, make nice opening. And a little bit over here, and a little bit over there. Okay, now we can just clean up. And these blue relays, these are high resistance read relays. High isolation, and this is a footprint for DS2E ML2 latch-in relay, like this yellow one around. This calibrator using lots of them. They are nice relays. It's too bad that manufacturers obsolete them. That's the typical challenge for the test equipment that survived long past the anticipated obsolescence. So this calibrator was designed in late 80s, but it's still not beaten even today. Even by original manufacturer Fluke. They made 5730, which is only slightly improved performance compared to 5720. So all the progress in digital processing and everything is not very useful when you're trying to have the ultra high performance analog circuit design. There are some improvements, but definitely nothing to enable us having much better performance than this 1980s monster. So we don't have 8.5 digit calibrators. We're still relying on 5730. We have all the resistance, all the DC voltage performance and specifications of latest and greatest 5730 are exactly the same as 5720 that I'm repairing here. So relays are in place. Now I can solder in. I put this shield so I can put the board upside down without applying pressure to these resistor networks that we have, because they are on ceramic base and they are easy to crack if they are force applied. It's not solder. Looks like this live stream is kind of sleepy, boring one. I don't see much people participating in chat, which is fine. I plan to do these repairs on these boards anyway. I would be really happy if I can get this calibrator to be fully functional for main DC voltage outputs, such as like 10 volts, 1 volt, or like 20 volt, 2 volt ranges, and 200 millivolt, as well as all the resistance outputs, and maybe some of the base, like smaller currents, like 20 milliamps, 2 milliamps, and 200 microamps. And I don't actually need AC voltage out of it. I don't need high voltage or high current, because I have 2 other calibrators for that, and this would be just using as a daily test source. So if I can source very nice low noise 10 volts out of it and some resistances for resistance transfers, that would be just a bench unit. So I can do various experiments with different circuits using Calibrator just as a fancy power supply essentially. So I wouldn't be calibrating multimeters out of it. It's just like a fancy source. And also, as a primary purpose of it is, if I have good working boards, then if some of the boards go bad in my main calibrators, then I could use this as a test unit to either repair those boards or just take the boards out of this calibrator and put in my primary ones, obviously after full recharacterization. So instead of having a bunch of dead boards lying around collecting dust, I could have something useful. So that's the main idea of this project. And we can also try to experiment with different circuits. Try maybe like more modern lower noise op amps for current outputs, and provide guarded current output on that triaxial port that I modified and installed previously. I have actually an article about replacing that M connector for wideband, which I have no plans to install in this calibrator, into the triax port, because original 5700 have the actually capability to supply guarded current, but only if you're using the rear terminals. So if you're using front terminals, there is no such option. So like electronics in the calibrator is capable to provide guard for current, but not in standard configuration when you have front panel terminals. So let's clean up a little bit more. I like these shop towels for cleaning flux because they kind of disintegrate while in process and taking away all the contaminated bits. So cleaning pretty nicely. And then I just need a little brush to wipe the excessive paper towel out. Easy peasy. Or I can just put in the fume extractor and then it flies away. Okay, I think this is good enough. So we have relays installed. Let me show you. A little bit on how you're doing, but should be fine for now. So, and these are the good networks, so we'll need to populate Z1 now. And this is that 100 mega ohm together with all these networks and this 90 mega ohm with the 10 ppm per degree coefficient, we get 100 ohm output. All right. for the calibrator, well, yeah, 4700 is nice. I have 4808 as well, which I do like, but my daily drivers are still 5720s. I can show my current setup in the lab, just as a little break. So let me flip some lens. To show what's going on in the lab. And there we go. OTA? What's the OTA? So there is my 4808 hiding behind some of the stuff. Let's actually move the there we are. So it's fully optioned 4808, except the wideband, and I don't have the 4600 amplifier because I don't really need high currents every day, and I have 5725 for that. Then I have 1281, then that's 3459 project, that 3458A with 11. So this is still work in progress. For right now, I'm testing IDC stability in it to make sure everything is good before we continue with the modifications and future crazy ideas. And we have my friend's 5790. Then we have the 2510 that is controlling that little temperature chamber. That little guy is just a random test 2002. Nanovoltmeter under it. My two main 3458As. And there are a bunch of these boxes. So this is 792A. So obviously I have one there. That's the power packs, essentially just a power supply with the batteries, and then the actual units, transfer boxes, one over here and comparing with one over there. So that's how you compare two AC standards. There is a T connection and then the nice cable going to the calibrator. So that's my primary calibrator, 5720. That's where everything is calibrated against from. And everything, I mean like DMMs and stuff like that. So there is a high resistance bridge, that box with the blue cover. 3458A for the high resistance bridge. And actually I need to hit enter on the thermometer. That is monitoring the temperature inside of that big thermal chamber. It's a Peltier controlled programmable thermal chamber, air bath. So we have the calibrator with the amplifier for it. Then I have a secondary check calibrator, also 5720. It's a happy box. And then we have the smaller temperature chamber which have I usually have a big one to have fixed 23 degrees, and all the resistance standards are just sitting in there always, even if not measured. And then in this smaller chamber I have DUTs, and then I can program this second thermal chamber for different temperatures to measure like temperature coefficient, stuff like that. It's only 40 watts, so that's all it is able to get from 2510 Keithley. And then there is another resistance bridge right there, Measurements International 6010. That is for resistances 10 kilo ohm and below, as well as my other friend 5790. So that's the current setup, and I was doing, and I'm still actually doing AC voltage calibration tests using these two 792s. So that's the latest addition to the lab, I guess. It's not easy, not the easiest box to use, but it's quite interesting. So maybe eventually there will be more details posted on the site about it. So that's it for the calibrator tour. And this guy is just sitting right in here. And all the bench with all the stuff. And a bunch of lights over there. And the battery died in camera. So let's swap to another view. 6010 is actually not that expensive. The calibrators are. So the calibrators are usually brand new right now is around 80 to 90,000. So obviously 57 old 5720 wouldn't be that expensive, but it's still enough to buy a decent car. And brand new 6010 is cheaper than brand new 5730. Not much, but still slightly less money. And obviously 6010 is a very specialized kind of piece for resistance measurements. So it's not going to be as universal and useful as a calibrator in a typical calibration metrology lab. Obviously, that's why you don't see much of them outside of the really big labs or outside of the labs that focus on resistance metrology. But calibrators, you can find plenty. Alright, I guess it's enough slacking around putting those resistors in. So let's get on to our main task at hand. .4808, yes. Essentially, that run was took the 4808 design and looked at all the possible improvements, and that's what they did. And they replaced the front panel, that slightly ugly black front panel with the filament lamps indicators, to a more beautiful VFD based front panel, which have big nice LEDs. My 4808 is most of the time is off because the summer is coming and temperature is getting higher, so I don't use it most of the time. So it's just heating turned off. But when I was doing some resistance measurements, I did have it to run a few months. Okay, so we're ready to start putting our stuff in. Let's see if we can just plug all these resistors in. $171. Okay, and now let's do from other side. 900 ohms. Now we have 90 ohms. Now we have 10 ohms. I have actually too many pins. Did I miss some? Let me check. So let me see. So this is 900 ohm. Then we have two connections to the 90. And we have two connections. Okay, I think. One, two. See the schematics. One, pin 2 and 3. 2 and 3. 4 and 5, 6, 7, 8, 9. Okay. So the 10 ohm, should be two connections from 10 ohm. And then we have maybe I'll just redraw. Slightly different way. Okay, I think I get it. So then 900 ohms should skip one pin. Do like that. And then, or actually no. There is 90. Have too many pins somehow. So this goes to those three and goes to another. Pin 4 and 5 connect together. Yes. Pin 6 and 7 connect together. So we have 3. Oh, okay. Got what's the confusing part. I think this 19 ohm goes to 2. Yes. Okay. Can deal with this. It actually doesn't look too bad. So we can do something like that. It's like a broccoli, resistor broccoli. It's probably $1,000 in those resistors. Well, maybe not as much, but definitely not cheap. So I'll try to push the resistors a little bit in. Like so. So let's see that all the values are correct. So pin number 1, 900, connect to pin number 2 and 3. So I'll just jump there, 2 and 3. Then we have 90 ohms. Yes. Connect between pin 2 and 3 and goes to pin 5 and 4. Okay. And then we have 10 ohms going from pin number 4 and 5 to pin number 6 and 7. So there would be a little loop to go like that. I believe I can do the loop. Just solder a small pin in there. Then we have 19 coming from pin 8 and 9. So 1, 2, 3, 4, 5, 6, 7, 8 and 9. Same way. And then it goes to 171 and then it goes to 1.71K. Yeah, this looks okay. Well, let's do it. And there is also no guard around these resistors, so that would be in normal situation. I was wondering if I would connect all the metal cans, but since the Fluke didn't do that, we can skip that part too. So now the question is, I'll solder the pin from the back and then apply some solder from the top so it would flow into the pin. And I believe I need something to keep the board standing. Yeah, this will do. So let's go ahead. I don't need to solder all the pins, just some of them, so the resistors wouldn't move when I start poking them around from the backside. Come on. All right. It's a little bit challenging. Yeah, probably solder from the top. It's important to keep the time short, maybe like a couple seconds, not to overheat the resistors. All right, let's cut the pins. Now we need to restore the connection to these two pins. This is pin number 8 and pin number 7. So I'll poke the piece of the cut pin through there and solder it to the resistor. This will be an interesting challenge. I think I'll have to do it under microscope. Ouch. Actually this, yeah, okay. So I can show you in a sec. So those two sticking pins, they need to go to those legs near the 19 kilo ohm and 10 ohm, and 19 ohm and 10 ohm. So I'll just bend them, one to the left, one to the right, and solder to the pin. That's, I guess, as close as it's possibly get for 4-wire connection. And yes, there is a guard board, so the guard board is right here. It's actually a replica that I built some years ago. This part is not conductive, and this part is metal. I think I have like maybe 20 of them. So if anybody wants one of these boards, then subscribe to my channel, I guess, and then I can send you one of these boards for free. So just let me know in the comment your email, and I'll contact you to one of the souvenirs. So there are 10 of the boards waiting. So they are manufactured in 2018. That's when I made this design. How long I was waiting for these resistors? Well, as usual, about a year. Custom values take from 9 months to around a year when you order from Vishai Precision Group. So it was always like that, even before the shortage of electronic components, which is okay. And the reason why I say it's okay, because you are ordering custom parts, and usually the quantity is very low, so they will need to do all the custom processing. So that takes time, and then they will retest it, retest the chips. You can order a lot of customization, and this all takes time and cost a pretty penny. You can do the same even for the op amps and stuff like that. Obviously you will not be able to order like one op amp customized by your needs, but if you are a big customer and you need some specific parameters that normal op amp is not quite achieving, you can customize and order your specific op amp for your project. Obviously it will be cost thousands and thousands in such stuff, but it's definitely possible. Alright, I think that's it. So I have the resistors installed. And we can plug it in and see what it does. So let's clean the box. I'm pretty sure like these resistors are much fancier and much more stable than original ones. So maybe we even improved our specs. We'll see. The little bit concerning part was that Calibrator wasn't able to output 1 ohm and 1.9 ohm, which come from that another board. So it's either because the resistance path coming from this board as well, or maybe there is some other relay issue somewhere on the motherboard, for example, like 4-wire connection. So let's plug this one in. And by the way, that board, there was a question where that board goes. And that board goes on the back of this PCB. Like you can see these mount holes. And this out. The line, where is the? There. So you have all these holes to match the pins for the relays and match for the pins of the networks, and then 2 screws go screw that on the back, and then that's it. This is how this board is in all 5700 and 5720s. And actually these standoffs are quite tall. They are taller than the resistors, so maybe they had the provision for the cover. But like I never seen any calibrator, and I seen many of them, that would have anything like a cover in here. We can 3D print some cover, for extra air buffer protection, but Fluke decided that it's not necessary, so that's it. So that's where that board is, what it's for. But obviously for now we can just test as it is. So let's plug it in, see what happens. Okay, port is plugged in. Clickety clock. Let's see if it's detected. Ohms module, it's not detected. Or maybe there is no separate detection between the ohms calibration and ohms module. That's interesting. Let me check on the actual working calibrator. That should answer any of our questions. Let's see. So there is ohms module. Yeah, it doesn't have separate for different boards, so that's fine. I guess we can switch to our 3458A and see if we can get any resistance outputs. Maybe I can doctor the screen so I can show the both. Let's see if I can do that. That's not that. Sound okay? Yep, sounds okay. Okay, that's this. Our meter. And my webcam. Let's add the webcam. Very There it is. Okay, I guess this would work. And maybe I can kill some light a little bit so you could see. Is that better? I guess so. Some reflection. There we go. Anyway, let's output 10 kilo ohm. External guard, external sense, operate, and we don't have the reading. So the DMM flipped to some value. Set compensation enable. Okay. Current exceeded, so something failed. About 1 kilo ohm. Nope. 0 ohm. Okay, there is 6 something ohms. It doesn't look right. About 1 ohm. So lower the shop. About 2 wire. Nope. So something seriously bad. Let's run a self-test. See what happens. That's fine. We don't have that board. Don't have that. Don't have it. Don't have it. A16. Don't have it. Now the interesting part is that 1 ohm and 1.9 and 0 ohm short connected, they come from A9. Have some strange smell. Not smell, but maybe we should get the thermal camera and actually hook up the board on extender and see if there is anything heating up. Let's try that. Let's see if I have a HDMI cable. Well, I do have, but it's short. Okay, let's try it. And 12 not responded, that's fine. see if this works. Okay, well, no self-test errors. Let's see. I need to construct some setup. So I have a pair of extenders. Let's see. I think it's we need to test the A9 first, which is a little bit a problem because it's facing the other way. Okay, let's do the A10 since it's straight in front of us. So I need to cut a few extra pins. So this is the extender. I actually have the PCB way making a new extender for me. These ones I got 2018. And I need to chop a piece of plastic for key. Bodging connectors, so I can have them to plug in into the motherboard. There is a version of these connectors. This is D41612, I believe. Connectors which are keyed, so there are notches that match the pin on the other end. But these connectors not supposed to be like that, so we need to mutilate them a bit so I can plug the other way around. So this is how you, this is just one-to-one straight connector. Now we need to plug it into the board. Easy peasy. Now the board is standing up. focus on it. See if anything hits up. Okay, I think this is close enough. So can power it up. Unit is on. Initializing. Okay, it's on. So I don't think anything is getting hot. Doesn't look like. I see there is this, what is it, op-amp? Yeah, that's just a reflection. And I think this is just a reflection of the resistor top. So let's try to output 10 kilo ohm again. Oh, no change whatsoever. Let's try 100 mega ohm, because that should activate the read relay. It's not latching, maybe it will heat up a little, but I don't see anything. And I don't see any of the resistance output. 3458A still says 1 giga ohm. Not 1 giga ohm, over a giga ohm. So it's definitely not doing anything. Well, that's an interesting problem. There is nothing much on this resistance board other than relays and a bunch of resistors. So yes, I can try to step through all the values. And we can take a look on the other board with the camera. So let's try another values just to be sure. And all the wiring and connections, they look correct. So this is 100 mega ohm, 19 mega ohm, operate, nothing on the meter, 10 mega ohm, nothing, 1.9 mega ohm, nothing, 1 mega ohm, nothing, 190K, nothing. And these values, by the way, generated by using those other resistors, I think. Oh, hold on, I'm stupid. I know what's the problem is. I didn't do the shorts connection between all those Kelvin points. Oh boy. So essentially there is no continuity path. Like how it generates all the high resistances is connecting either sections of these networks into one kind of chained resistor. That's how they get optimized resistance values. Okay, let's reconnect the stuff back, and take the board out and restore the missing connection. I think that's what the problem is. Let me flip the recording stuff in camera. Rookie mistake. Where the hell is my mouse? Come on. So the problem is, I'll show on the schematics. Probably on this representation. So I have the connection done from here, like you have soldered resistor here, but I don't have this pin from connected to this. So between 90 ohm and 900 there is no connection, and same with all the others. So I did the connection here, these two and these two, but not the other ones. So half. Thermal camera is let's see, it's a TIX 560. So I just need to have some shorts, then we will be good to go. Or not. And I have just a tip for that, and obviously you cannot see anything because of my microscope is in the way. So let me find my favorite tip. There you are. Okay, I think I Dropped it somewhere. Yep. That's my favorite tip. It's a 45-degree sharp cone. Very nice to get into some narrow spaces. Doesn't have much quality, so you cannot use it to solder like heavy stuff. In this case. There we go. Doesn't want to get in place, just like no. I need to take a break. Yeah, I guess I got that one. Let's try another one. Well, got another one, and I think need two more. I'm trying to hit the little copper bar, which was the pin of these resistors, the one that we cut out earlier. So I get it hot, and then I kind of lay it on the resistor pins and make sure the solder flows between two resistor body. Little bit too close. Let's call it heat treatment for the precision. and I have the soldering iron set at it's 250 degrees Celsius. Whoop, there you go. I think this is too short. Now we're talking. Oh yeah. I think I got it. A little bit dodgy, but that's a proper connection. Should we try again? Would be hard to clean all the flux in between the pins now. Okay, let's see if it works first. Those pins are pretty tall. Okay. I don't think there is any point to bother with the extenders for this PCB right now. So I'll just plug it in. And let's power it on and see what happens. Thank you. Look at that. 10 kilo it is. It's a little bit high, but I actually don't remember if I calibrated this DMM or not. But we get the reasonable output, so let's try other values. I would say that's a progress. let me see if I can turn off some lights. This should be better. There you go. Let's try 19 kilo ohm. Okay, got that. 100K. Got that. 190K. Okay. Okay, 190K. There it is. 1 mega ohm. There we have 1 mega ohm. 1.9. Yep. 10 meg. Yep. 19 meg. We got that as well. By the way, this is all 4 wire. So 100 mega ohm. We need to have 2 wire. So this is 100 mega ohm, and we need to switch actually. Oh, this is actually 2 wire. Okay. Let's switch back to 4 wire. And then go 1 mega ohm, 4 wire. Okay. Let's do 100 kilo ohm. Okay. 10 kilo ohm again. Okay, that's better. Closer to 10. And let's go 190 ohms. Yeah, we got that. 1.9 kilo ohms. That's pretty good. 1 kilo ohm. It's even pretty close to 1 kilo ohm. 1.90 ohms. Yep. 100 ohms. Okay, we got 100. We got 19 ohms. Yep. 10 ohms. 1.9. Okay, that works too. 1 ohm. Works. 0 ohms. Also works. Let's try self-test, I guess. So resistance to be working. Let's do the self-test, run diagnostics. I would say that's a working resistance. So, question, will it calibrate? Because most of those items, the resistor network on the A9 board is related to the calibration functionality and 2-wire compensation. So we can try 2-wire compensation. If that works, then we can try to calibrate the calibrator to see if it actually can complete the procedure of adjustment internal resistances without error or fault messages. Okay. Continue. Okay, no self-test errors. Let's do the calibration 0. Yes. While this is running, we can swap the wires to 4808. So that will be our calibration source for this test. And then we can try to calibrate. Okay, so we can configure to 10 volt output, and then when the calibrator asks the 5700 Hulk-3, then we can input the desired value. So we will need 10 volt, minus 10 volt, 10 kilo ohm, and 1 ohm. Okay, it actually did pass the calibration 0, so that is interesting. Let's go and do the cal. It actually gives you a warning, so it has only been 12 minutes. Do you still want to calibrate it? Yes, do it, because usually you need to warm up at least like a day or so before you can have the best uncertainty calibration. But obviously right now we don't care about that. We don't care about accuracy at all. We just want to check if it's functionally working or not. So calibration, ambient air, 23 degrees. So external voltage, we have 10 volts, actually just 10. And let's see, check the cables. Everything looks all right. So we need to enable the output on the 4808. Positive. And now we can calibrate. So first it's usually measuring the internal ADC gain together with the DAC against entered value, which in our case right now 10 volts. And then it will apply that correction to estimate the true voltage of the references and true voltage output of the DAC, REFDAC, that A11 assembly. And it's obviously need to do it in both polarities and multiple ranges. So that's what it's doing when you're doing external calibration against 10 volt. And then for linearity check, you need to do the adjustment using minus 10 volt. So usually that means you need to swap the wire, so plus to minus, minus to plus, without actually altering the calibrator or source. Because if you just program in the calibrator, like I will do right now, the output minus 10 and plus 10 could be a little bit different, and that would propagate into an error during the adjustment. So usually it's the best to flip the cable without altering the settings. But for the functional check, it doesn't matter. So the resistance repairs so far is looking good, and obviously it will need many more measurements, temperature coefficient measurements, using the ACAL measurements, comparing with external bridges to test that everything for resistance works at least the same good as the original spec. So there could be still issues hiding, but functionally it's already looking much better. I'm pretty happy about that. And I will document most of this stuff. Okay, this is an interesting error. I didn't see this before. DAC appears not to meet linearity spec 2646. Maybe it's because the 10 volt is actually still warming up at 4808. I just turned it on. Let's try it again. I didn't see this error before, and this error is actually not related to resistance. 23, 10 volts. Let's go. 812 board is a AC voltage sensor board, so it have the thermal converter, actually two of them, and that's the board that is responsible for amplitude accuracy of all the AC voltage outputs of the calibrator. So A12 and A13, which is AC voltage output board, those boards are in tandem to work, giving all the lower voltage ranges for AC voltage and AC current, such as 22 volts AC, 2.2 volts and 220 millivolts, and lower ranges. And then A14, A15, A16 boards, they provide together 220 volt and 1 kilovolt range, as well as 1 kilovolt DC range. So those 5 boards are responsible for all the higher voltages. I do have the boards, but they are quite in a bad shape. Need to have a lot repaired, especially A12 board. It doesn't have the sensors because, like I said, these are the donor boards that I bought broken to repair my other calibrators. So there is a lot of problems with these guys. So this is the A12. A lot of missing components, so sensors, and they are here. Missing chips, missing controller, missing these 2 chips, missing this chip, a bunch of small resistors are missing, and this board is a 13 board. So we have the broken PLL loop, and the loop is quite complicated. All the components are in here, but like this is a faulty board. So that will be some future time repair if I ever decide to have this calibrator with AC voltage, at least basic ones. But for now, I just want DC voltage and resistance out of it. Okay, so the voltage calibrated. Now we need to have the negative voltage, so we just need to flip the polarity or flip the cables, which is a better way, but for now. So this is test adjustment test for -10, and after this step, if it's successful, it will ask for 1 ohm. And actually that's the problem, because I cannot source 1 ohm from 4808. Yeah, now I remember. So we will need a fixed 1 ohm standard, which is fine. I can still run from the chamber. So we can get 1 ohm. This is just 742A, 1 ohm. Nothing super special about it. It's one of my backup calibration references. So did it pass? Yes, it did pass. Now we need 10 kilo ohm. So we can source that from the calibrator. Resistance. 10K. External remote sense, remote guard, and output on. Okay, so we need to enter that value. So 10.0000 474 and hit enter. So let's see if it can actually adjust its own resistances. Probably will fail. Still going. Usually, like the full adjustment for the fully complete calibrator, using the artifact cut calibration procedure, takes around an hour. So it takes like these initial values. This takes maybe like 3 to 5 minutes. And after that, it goes all the automatic adjustments internally. So that takes about an hour. But obviously, we don't have the AC voltage stuff and higher voltages, higher currents. So this procedure actually much shorter when you have smaller configuration of the calibrator. But again, Fluke never sold any calibrators that were less than fully complete, except the wideband. So wideband was optional, but there was no like DC only or resistance only calibrators in 5700 series. Nevertheless, the firmware actually does support normal operation in those reduced setups, which is really cool. Okay, so it looks like okay, and our 10 kilo ohm changed 113 ppms. Usually this number is like 0 to maybe like 1 ppm with the normal calibrators, but obviously this was never calibrated with these boards, so doesn't really look that bad. Now we need to enter 1 ohm, and for this I'll connect the cable to the fixed standard. I monitor drift of this 1 ohm and using the bridges, and so far it drifts around 1.2 ppm per year, so not terrible, not wonderful. The specification is I believe 8 ppms per year, something like that, so still well within specification. Okay, 1 ohm is connected. Let's enter the value. Should be 100003507. Well, we cannot enter that many digits, so 351. Let's round it up. Okay, go. So in this test, Calibrator will source 130 milliamps into external 1 ohm, measure voltage drop, and then calibrate its own internal 1 ohm and its own internal 1.9 ohm. When it's doing 1.9 ohm, then it's sourcing around 65 milliamps or so. So that's the procedure. That's what how it is adjusting the value that it gives to those fixed resistors, card resistors on A9 board. Maybe in future we can replace them with some fancy Vichy bulk metal foil. That would be an interesting experiment to see if it's any better or worse. Yeah, other calibrators usually running some tests or long-term experiments or calibrating the DMMs. They are pretty often used every day, so that's why having this another source would be very handy, because for example for high resistance I need two voltage sources which should be quite low noise and stable over time and over temperature, and I cannot tie up both of my calibrators for high resistance measurement setup, because then I will not be able to do anything else when I need a source. So, and 4808 is not calibrated, not adjusted all the time, unlike those other calibrators. So that's kind of the idea. And anyway, all these parts, all these boards were sitting for like 4 years now. So it's better to have them working together as a usable device than just collecting dust, like I said before. So we actually did pass 1 ohm and 1.9 calibration. So this is a good start. Let's proceed with the calibration and see if it's actually can finish the full calibration. I mean full for this setup. And then we can output the take a look on the resistance, new resistance values, if it manages to get to the end. And then we can include this live stream, and I think that would be good Sunday. And I do plan to document most of this stuff on the article about the calibrator. So that would be a nice result. So I already posted some of the stuff about this calibrator project in xdevs.com/fix/Hulk-3. So I can show you just in a second. So this is the article. You are welcome to go through and browse through it. So this is actually the first calibrator part, and this is essentially everything that is broken in this calibrator as it was a couple years back. So you can see pretty much I have all the boards except the A14 board in that empty slot in the center. And this is the front panel, was originally from this calibrator, so had a smashed DMD screen. So I got a few other broken front panels. That was a saga on its own. All the fun stuff, some repairs, some little reverse engineering to make this board, some JTAG action. And this is another board, and we have some working front panel. The base setup. And then some motherboard repairs. I had to dig through multiple layers to restore some of the internal burnt wires. So that was fun too. And this is actually this A9 board that we were today fixing. So I will update all the article stuff in here. A19 board. This is some repairs on A18 with a blown hole in it. And some of the pictures are from the calibrator boards from the others. So that's it. So enjoy the read. Calibrator is still going. Is it possible to turn display off? Simple answer, yes, but not by the normal operator procedures. So, in theory, yes. In practice, not really. But again, like for 90% of the time, I just communicate with the calibrator remotely over GPIB. It's only making the repair difficult because if calibrator locks up in some fault, then it will not be talking to you over the GPIB as much. And some critical faults, it will hang up on the bus completely. So that's why I went through trouble to reverse engineer and actually get that board working. I mean the front panel board working with the both screens, so I can see what's going on. Until then, this calibrator was pretty much just sitting with the boards scattered all around the lab. So I guess I can hook up this calibrator outputs while we're waiting to the DMM again, and we can compare the readings. We can actually use Keithley 2002 because I know it's calibrated. I don't remember if I calibrate this 3458A project unit before or not. Not all 5720s turn off the control screen after a timeout. Only new firmware, new version front panel and new CPU board in combination do that. So none of my previous old ones, old front panels, do the turn off on the control screen. So that's that. So let's hook up to the Keithley. I think the cable is long enough. Well, not really, but I can do a little bit longer by moving the calibrator a bit. Well, this one is long enough, but slide it a little bit. Okay, I don't think I can slide any longer. Yeah. Well, I guess I can use the shield for the positive. There we go. Still a wire, right? Still running through the calibration. Right now it suggests its internal value for 10 ohms. Will it pass? Most of the time in the calibration procedure is AC voltage related and AC current stuff, because need a lot of warm-ups, a lot of time for warm-up, and also a lot of frequency points. Now it's testing 1 mega ohm. And obviously right now the output is disconnected in Calibrator, so that's why Keith is just showing the random charge going up and down like that, so that's normal. Any high impedance DMM would be showing some random voltages on the high impedance input ranges. Nothing wrong with them, this is how they designed to do. So that's all normal. Now we have calibration for 10 mega ohm. $19 mega ohm. 100 mega ohm. I think it's almost done. Okay, now it's testing the current. So this will be an interesting point, because if any faults at A7 board which generates currents, we will catch it now. These steps, adjustment steps, were not run before because we didn't have the resistance boards, but now we do have them. So we'll see if this A7 board actually good or not, together with the resistances, of course. So far so good. (220 microamp). This range is not very great at on these calibrators, so that's one of the area of improvements I would like to experiment with in future. It's kind of a reason why I replaced the connector from the N connector that is not connected to anything without wideband option to the isolated triax, so I could try improve the noise and performance of the low range currents, which can be useful for calibrating high resistances again. I think it's almost done, because we don't have 220 milliamp. Actually, we do have 220 milliamp. We don't have 2.2 amp range, because we need to have AC voltage modules and high voltage, high current modules for that. Maybe eventually I will get the A14 board missing in this unit and make it complete, but like there is no such goal at this time. Even the chassis enclosure is not really 100% original, because the rear metal work, I didn't have it, so I just made the custom metal work replacement. Okay, calibration is done. So we have largest change 3000%. What is it? 3800% of the specification. That is fine, because it was never calibrated with these boards. So store values. And we're done with adjustments. So now we can source some voltages. Let's try that. And see what our Keithley says, if it's going to agree or not. I think this A11 still have some issues, so let's try 2 volts output, and we don't have any output because I probably messed up with the wiring. Let's check again. We have black wire. Yeah, looks. So the orange cable. Oh, okay. I see what the problem is. This one actually like so. Wrong cable for 4-wire. And then this one was like so. Now I need to flip in here as well. I guess it's a little bit late already for this boring live stream. Okay. Okay, we got almost 2 volts, but it's far off. Shouldn't be that far, but so that gives us the hint that a DAC problem still is there, and it's kind of close, but not really. So it's pretty much 43%, 43 ppm of the value, which is it's like huge for a calibrator like this. We will need to do more repairs, which is fine. So let's try other ranges. 200 millivolt. Yeah, also off. And 20 volts. Yep, that's way off. And negative. Okay, so it's not even the same. But again, we use the calibrator to calibrate the unit, so it's given all the different values. Anyway, let's try resistance, because that's what we come here for. Obviously I need to switch the DMM for wire resistance. Let's see if it agrees. It's pretty good actually. So we have on the calibrator 9.9999, 12 kilo ohm. And on the DMM, it's pretty much spot on. So we had 20, let's say 20. So that's 0.8 ppm. That's pretty good. Let's try 1.9 kilo ohm. Does this work? Yeah, it's doing something. Okay, let's try 1.9K. So we have 1.8999967. It's a gain. So we have 20 on the DMM. So that's around 25, around 2 ppm, 2.2. I would say that is pretty impressive, given the non-native resistors and all the bodges. Let's try 1 kilo ohm. 3 Calibrator says 351. We have 324. Looks like it's all around. Here is also minus 2.7 ppms. Let's try 190 ohms. So we have 500. Okay, this area is much bigger. So that's around 10 ppm. That's a little bit too much. Yeah, usually this is smaller. So okay, 10 ohms, 100 ohms, 999, 9, so 8, well 900 something, around 7 ppms. Okay, also not that great. 19 ohms, 999, 8, 7, 702, so around 18 ppms. That's a little bit a lot. Let's try 10 ohms. And by a lot, I mean like what I usually get from the other working calibrators. Deviation between the ACAL and actual value. I'm pretty sure it will still meet the spec. Let's see, spec is 20 ppms here. This is 24-hour spec. And we are seeing right now 23 ppm without the covers on, without the proper warm-up for calibration, so I think it's fine. Just need more testing. 100 kilo ohm. Okay, so there's also a little issue with this knob, which I will need to rectify. 250, so around 10 ppm. So it's like on and off. Some more testing will need to be done, but I think that's it for now. We can try some current and call it a day. 2 milliamps. Normal output, and for currents I think I'll need to use a different DMM. Yeah, because the wiring is different. I don't have the proper binding post on the terminal on this Keithley. We can just use 3458A, I guess. That's fine. I hate bananas. So inconvenient when you have all the other cables and all the other connections and devices with the binding posts. Let's go to the big range. And see if we get decent currents. Okay, 1 milliamp. Looks all right. Some offset. Yeah, that's a lot of offset. Interesting. These values shouldn't be different. Okay. Maybe that DMM is needs some calibration too. Anyway, we didn't blow up anything yet. So, everybody, thanks for watching.